computer. Yes, we are recording. Hi, everyone, people online who happen to stumble into this channel, and people online who hear for a good reason. This is a paper from a new Japanese startup, relatively new. I think they're 3 years old, and again, startup. I don't understand now how they call those companies, because it's primarily research oriented. My understanding, it's more like we would call DeepMind a startup in 2015, 14, although it wasn't offering any product or even trying to get any product. Every country needs their own AI, and my understanding, Sakana AI was founded by interesting people for that reason. So it's Japanese AI company, basically the Japanese AI company. But they started with a very interesting kind of goal or motto. It is not about, like Yaron was telling recently, that everyone is looking for people who can do LLMs. Everyone just LLM. And they're not about that engineering of what's already working. They're about exploring, like real research, exploring new stuff that hasn't been tried before. And well, there's nothing new under the sun. But at least they're not digging the same turf that everyone is doing, everyone is digging. So they published many papers in just 2 years. I think they published something on neural evolution and on like this alternative approaches to doing AI. And this specific paper is very interesting to me, because actually this will be a part of my lecture, 1 hour and 30-minute lecture, like proper 2 academic hours on, and it's, I think, lecture 4 in my 6 lecture series that I'm working on dynamical introspective models, which we ourselves with Marinal have published on and working on. So it kind of falls into this category of systems that self-introspect and assess their own confidence, etc., etc. But I won't talk about my stuff, although I will talk about historical stuff. So motivation. What are we doing? So motivation of this paper is the following: animal brains are highly dynamic and time dependent. Look how this lion adapts to the error in their differential equation solver once their prediction changes doesn't track the reality. So the lion changes trajectory, like they were chasing this, and then they dynamically, with the observation, they adapted. And humans and all animals do that. We adapt constantly. My motors are faulty, but I can track the movement of my hand. If I close my eyes, touching my nose, with age becomes increasingly difficult because my motors becomes faultier and faultier, and it's harder to correct. And we constantly self-correct, like with Euler method or with like any other method. We don't analytically solve differential equation. And people argue that, oh, it's just a heuristic. Euler method is just a heuristic as well. You make a step, you check the error, you self-correct, you make a step, you check the error. So dynamic. But the motivation of the authors of this paper, they chose as like, oh, if we want real AI that works as good as the brains do, we need to do what it does, be more biological, which I don't necessarily agree with, because, well, I have another reason. I think evolution is an optimizer, and it found more basic underground reasons, like the foundational reasons for doing it this way, because computation is more general than functional approximation. Well, in the limit, when your functional can be infinitely wide, infinitely deep, you can do any computation with that single function. But given a resource constraint, doing computation, click through step by step, is more efficient. And learning a computation is different from learning a function mapping. For example, a recent paper that I will not talk about here today, but it demonstrated, from another group, demonstrated that transformer essentially learns a heuristic or a function for every length of the input. The length changes and it encodes a new heuristic. That's why you accumulate a lot of parameters. While with a dynamical system, if you're learning a computation, and this paper will address that, you're learning a thing that can be applied for any length of sequences. Like if you learn an algorithm how to add numbers, that's it. You just have to keep applying it. Doesn't matter how large are the numbers and things like that. But transformers, practically for every length, they learn a different algorithm, different stuff. Well, okay. Well, anyways, and neural networks abstract away temporal dynamics, right? It's just a mapping. It's a function from inputs to outputs. Like the firing rate of neurons in the brain is temporal dynamics. Every neuron is a dynamical system. It's kind of like dynamical system all the way down, and then we emerge. So neural networks just say, okay, it's static value. A neuron just gives us an output instead of dynamical output. We have a ballistic system. Input generates a single output. That's understandable. We need efficiency over biological realism, which this paper probably, I don't care about biological realism. I'm glad this is not on the record. Right? But I mean, essentially, if we want to build a thinking system, AI, why would we care about biological realism? Maybe we can find, I mean, it's of course a little obnoxious, a little arrogant to say, but maybe we humans will find a better local minimum than evolution was able to do. I mean, but we are in one of the local minima, and we need to go further. But anyways, efficiency points back to the hardware lottery ticket paper by Sarah Hooker, where basically there may be better methods like algorithms, like what the brain does, but our hardware favors transformers. So transformers, everyone does LLM. But yeah, that's what this saying, insufficiency over biological realism, which, I mean, okay, anyways. So, and then what we want, brain relies on STDP and oscillations, spike-dependent plasticity, spike timing-dependent plasticity, when the timing wire together, when neurons correlate, they tend to connect and establish stronger connections when the time series correlate better, stronger. And oscillations, why don't we model that, right? I don't know what to do with this. Missing temporal components, yeah, there's no temporal component in our models, almost, of course. There's nothing new under the sun. And in human cognition, there's always temporal components. We're thinking a thought. We're not just looking and recognizing. We do have that look and recognize quickly system. It's a visual system. We recognize faces that quick in one glance, and threat and things like that. But mostly we are scanning the environment. There is a temporal component to all of what we do. So the claim of this paper and the authors, I guess, is time must be central to AI. I agree, but I think they're doing it for a wrong reason, or at least claiming. So let's build a neural network model that is as dynamic as this Plis brain. That it can act sequentially, and it can self-correct on the fly, and it can change the time. Like if the lion already caught the pig in the first linear stride, the lion doesn't need to do anything else, right? But if we train a large transformer to do this, even though the pig is already there, they caught it, the transformer will keep computing because it has to finish the computation. That's how it's built. So neural level temporal processing continuous thought machine, the paper that we're talking about, introduces this. Let's do at every neuron, it's time processing. Neurons synchronize or desynchronize. Let's represent their synchronization as a latent space and work from that latent space that make our predictions and transformations. We want to capture essential temporal dynamics for the problem at hand. Even if it's a static problem, as I said, we're scanning with our eye, looking for where is Waldo, like in the busy image and things like that. We're not like, oh, I see it. Although sometimes that happens. Yes, we want sequential thought on any modality. As I said, image doesn't look like sequential modality, but we humans approach it as sequential. We approach everything as a sequential thing, sequential problem. Or spatial, but that's the same, actually.
So what you're talking about has been kind of looked at with neural ODEs, right? Or is that something kind of different?
Yes, but neural ODEs themselves are derivative. They're not new. It's recurrent neural networks. Or dynamical process, x equals f of x. That's basically, yes. And neural ODEs are retelling of the previously discovered story of continuous recurrent neural networks. Basically, people discovered it. Anyways, so, but yes, there is a relation with all those models. Neural ODEs is one of them. But we want to do all of that computationally tractable. That's the paper is trying to do. So let's see what they did. But we had something similar with recurrent neural networks, by the way, exactly. So this is a recurrent neural network from 2017, black or white, nothing was too visible, so I chose black there for the citations from Google. When deep learning with ImageNet, with AlexNet CNN started in 2012, the first actually super successful model in production for Google and everyone was an LSTM, a recurrent neural network. And Google Maps became much better. Google started to understand speech much better, etc., etc. And RNNs were used everywhere. So this is an RNN sequentially generating house numbers. Because of Google Street View, you have a lot of houses with numbers on them, but Google Street View from those video images of a car driving through a street needs to figure out the map. It reconstructs the map. So by collecting a lot of data of house numbers in the wild, these people, Voina and others, they build a generator, like a GAN or any kind of generator. You like diffusion now is popular. You sample a random vector and it generates you a number. The draw also does it sequentially, an even earlier method. It's an RNN from 2017 that generates MNIST numbers all at once from a random sample. You sample randomly a Gaussian noise vector, like you do in diffusion and stuff like that. And from that, it initializes and sequentially covers the image or images. You will see why I am doing that, why I'm showing you this whole idea. So this paper also, this is continuous thought machine that does sequential exploration. It is trying to get to green point from red point. And red point is you put a red point as a starting mark, and then it explores up to a certain depth and finds the best solution. You move the red point there, or the model moves the red point to the best so far solution, and it starts exploring further. And that's how it traces the maze and finds the solution. It needs to go from initial red point to the green, and once it got to green, done. It's found the solution. But it doesn't find the entire trajectory at once. It is walking around and exploring. So think about you being in a maze and moving your base, like again, coming back to the space and exploring it, then eventually, okay, it finds the solution. Okay, one more thing is, okay, their biological inspiration, and making this presentation wasn't that difficult as, say, usual paper with a wall of text, because Sakana AI, the authors, invested a lot in publication, like media, the blog post, which I think I linked in my announcement in Slack. The blog post has lots and lots of videos, lots of animations, lots of interactive, and lots of drawing like that. I don't know, was it Nana Banana too, or they made it manually? But okay, like in the brain, the claim is we want to look at synchronization of each neuron. That's the biological inspiration. And then those are each of neurons, each activation of individual neurons in LSTM, and on the left there, and CTM, continuous thought machine. I don't know, reach structured, but yes, look that LSTM is a little flatter and reluctant to change. Each neuron kind of tracks what they decided to track, while continuous thought machine, each neuron is doing a lot of stuff. I don't know if it's good or bad. It's like at this point in my presentation, this figure is less meaningful than it will become. But even after we will not know why it is good. It's just the internal behavior of the model, like more dynamics. But I wanted to bring this up before we go further, because what I think we are looking at in this paper is yet another, not demeaning the achievements of this paper, and like we need to be digging in that direction, but it is yet another recurrent neural network of a very interesting kind. Like this is LSTM, long short-term memory system, and I don't know, have you spent enough time to figure out what this means in LSTM and in GRU, what each equation, each operation here? I know Pavel works a lot with RNN, so have you gone and suffered through like?
Not really, I think, but by looking at it, I think I can figure out some elements. It's like the first one is gating the propagation of memory state or something like that, I suppose.
Memory.
The second plus is something like a residual connection.
Well, okay, so, but if you would have suffered through LSTM, full understanding of it, then you would even more appreciate what's coming, because suffering is kind of much more. LSTM already looks complicated. I mean, in retrospect, when you spend hours and days on it, it's like, okay, it's simple, and this is how like GRU emerges and stuff like that. But if you don't spend hours on it, then, it's just a black box from the gods that I've been given to use, and I will do what they say. But so you should spend time and figure out LSTM. But now think about this. This is one single box that repeats through time. Think about it now, because it's going to be dense. They're going to be like, this is the entire, thanks to the authors, this is the entire working of the system. First, there is a synapse model, which is like MLBBQ, so autoencoder will skip connections, that generates next time point in the activation sequence. That those are funny plots, colorful plots that you see. Then a normal simple MLP takes the entire dynamics with a sliding window and produces its representation at one point and adds that to the history. And this is happening for each neuron. And then for each neuron, we compute synchronization, not just correlation, Pearson correlation, say, or inner like cosine product or something like that. And then those synchronizations are used in deciding what the model will output and what the model will attend to in the data, and that attention attended to part in the data goes back into this internal loop. There will be even less clear, but more clear picture. So this is without the video. We will come back to the video and you will understand what's going on. All of the 10 steps we will now go through. That's what the paper is about. Although the paper combines them into just 2 pages, it's easy. This is an input vector, and each box here is just a number, right? It's a scalar value for each neuron. This model is an autoencoder with skip connection UNet style, input directly to output, second layer to last -1, etc., with skip connections. So you take this input vector, Z has a dimension, time is always there, there's current time, right? Time is a tick, so it's like an RNN in this sense, and produces this output activation. We had held a sliding window history for each of those neurons. How do we start with that history? Initially it's 0, but no, we learn the initial pre-fill. Remember the last paper I spoke about, Titans? They also trained the pre-fill tokens, but this is like pre-fill sequence is trained. Then the sequence, this produces only 1 point, 1 value. The next one, you prepend it, and you take an MLP, like just a normal MLP, give this sequence to that MLP, and MLP gives you a value. Yeah, it is very busy, but like there is a reason for that. It's like very simple operations in retrospect. It looks busy, but then okay. And this MLP produces an output, and this output is the one that is actually appended to the previous sequence. This was sort of temporary next element. This will be the actual next element. And then, okay, we have post activations. Those are ZT plus 1, next element vector for each of those neurons. But we store the entire history because like we need to be able to slide our window, and we need to be able to compute correlation. This is a slide, like there is an entire history of each neuron activations, and there is a sliding window that goes into this MLP. Once we have ZT plus 1, in practice, we can loop it back, and I can't write, but there is this loop here, and we can loop it back forever, right? And it will either diverge or collapse or something will happen. There is no input to the system, and still it's a dynamical system. X equals f of x. So you compute next ZT plus 1. But the system, if it would only doing that, is not too interesting because it doesn't have any input and output. And there's this block that serves to take the data as input and to produce the output if needed. What we do there is we store the entire history of activations for each of the neurons, and every time a new sample appears, we compute correlation matrix, basically. If you have D neurons, internal dimension of our RNN, sorry guys, it does look like RNN to me, I mean, and it's a complement, it's not like, oh, continuous thought machines. So this entire state, the Z, has a dimension D. This matrix, correlation matrix, is D by D. You correlate you can correlate across entire temporal history of each neuron, of Z, vector Z. But it's not here. We will go through everything that I'm saying, we will go slide by slide, but I want the entire picture first. If you just compute the correlations through entire history, then your present time will get drowned more and more in the noise of the previous history. right? Like this line running in the trajectory, but trajectory is so long that this current input, even if it's widely changing and bringing information, wouldn't matter. So in order to counter that, we introduce exponential discounting. So the current sample is exponentially more important than the previous samples. So you discount the history, but continuously. You're not chopping it off with an unknown hyperparameter window. Then you have D by. Remember, we want this to be efficient, still computationally feasible. Then we have this correlation matrix, D by D, and we sample each point here. Each value is S sub ij correlation between two neurons, or synchronization they call it. It's right here. It's fancier to call it synchronization, of course, because then it brings us back to the brain and etc. But correlation between two vectors is fine as well and precise. We sample randomly, few of them. It's a symmetric matrix, so we only need the top part from this top. That's why it's green there. From that top part, we sample randomly few output correlations and few input or attention correlations. So they're not overwhelmingly quadratic, just a few, however many we need. And then we can produce the output at this time point t. That's what we see on the maze. The output is xy coordinates each time as you want, or you can iterate this for k samples before producing the input. It's a hyperparameter. And attention allows us to cross. Remember, attention's scale product. Or dot product, just a dot product between the data input. Data input are features. If it's an image, you run it through ResNet and take the embedding as your features at each location. If it's speech, it's speech embedding. If it's tokens, it's tokens. But then you cross correlate with your synchronization matrix projected into some space, input space, in and out. See. And then this cross attention or attention of your current synchronization state and the data, input data, goes and gets tagged, concatenated with your internal state. When you output, the dimension is smaller. So this is how data enters into the system, into your function. But if data is zero or it's not there, the system is still spinning. The dynamic is still evolving. It's still doing okay. Let's go side by side.
A is a matrix, right? So this is, how big is A? Is it, how long is the history that you keep of these activations?
It is D by M. M is a hyperparameter, whatever window size you choose. This here, the history, you store entire history. Like everything you do during the problem. Like when this maze is being solved, you store entire thing. But for minute to minute, sort of like the tick by tick operation, of course, because this MLP is fixed. It can only accept fixed. If we used CNN here,
Q is a vector.
yeah.
Okay.
It's just a picture. Yeah. Well, look, it's kind of it is a cube because we have history. We have dimension from the history, but you will see in the equations here. So synapse model that they call. Okay, think of it just like a marketing. We need to call it something to make it look like the brain. Let's call it synapse model. So it's lowest level interaction, and the lowest level interaction. But this is feature selector from your dynamics, I guess. It doesn't matter. It's a differentiable function, so the entire thing. But synapse model is you concatenate your internal state, like in RNN, in LSTM and JRU, you have the internal state and the input, conveniently called output, of course. But it's attention part. It's a cross attention with the input, but I'm using their notation anyways. And you concatenate it, you pushed it through this autoencoder shape. You don't train it as an autoencoder. You train it end to end with a loss that we'll get to. But it's just the shape is like autoencoder because you want I guess you want information bottleneck, that's why. And D is the dimension of Z vector. So you start from D-dimensional vector, you increase it by concatenating. That's a hyperparameter, how much you increase it, of course. And then you project back non-linearly into that same dimension. Unit style MLP shared across all neurons. All neurons, well, of course, I mean, those are neurons. So the neurons are mixed here. So it's not only in synchronization, but here the neurons are intermixed as well in this synapse model. So it's all-to-all connection. Every neuron through this model is connected to each other. So it's a dense network of neurons, unlike sparse network in the brain. But okay. Then the words that I already said, well, okay, you call it pre-activations, just to confuse people, smart, unneeded words. It's like, yeah, there's nothing, I mean, nothing complicated there. And okay, drives the recurrent dynamics at each internal tick, of course, because that's the only thing, well, I wouldn't say, yeah, that's the only thing that makes the next prediction. But then we have again, it's very similar, Pavel, to what you do, because you have the interaction between time series, instantaneous, and you have within time series predictive model, like a one-dimensional here. But yeah, that's unrelated to people listening about the paper. So next step, pre-activation history. It's just a sliding window on the time, on the individual time course of each neuron. So you take a sliding window, M is a hyperparameter. One-dimensional now in this sense, because each vector, each neuron, well, okay.
I think each small.
I mean, it's confusing. This notation, I'm sorry about that. This is a column at each time point for all neurons, but rather the picture shows us a row of this matrix for a given neuron across all time points up to, from m-1 up to, from t minus m up to t. Yeah, here, t minus m up to t. So if you think about row of this matrix, here's what you're seeing here. And then, since you predicted this new point, this AT point, you're adding it here, like the last point. On the video, they emphasized it, they showed it. And apply an MLP to this point. Rolling window of the last M activation. This MLP is neuron specific. Each neuron has its own hyperparameters, neuron memory for the recent inputs. Okay, now, okay, we got here. Oh, this was only about construction of this. I should go faster or slower. How am I doing in time? Neuron level models, it's just this MLP. And this MLP, every neuron D has its own private weights, depth 1 MLP of weights D hidden, of course, processes neurons pre-activations, replaces static ReLU with learnable temporal function. Okay, we've done that before as well, but that's good. So it's a non-linear transformation. Then post-activation, so now we produce new ZT plus 1 that can immediately go back into this recurrence. Right? There are two loops in this model. Feedback loops is what I'm interested in and what I think is the future. At least without feedback loops, we will not get adaptive systems. And that's why I'm excited about this paper demonstrating this. They're not necessarily demonstrating the most powerful model, the most performant model, but they're demonstrating an architecture that is different from the current dominant one, that works on different principles and still performs quite well and interestingly well. So output of all neuron level models stacked into one vector. Okay, concatenated with attention output to right here to 4 input again, and this is latent state that evolves tick by tick again. It's not continuous time like neural ODE. Neural ODE, you can assume that the time is continuous, and then you just use an implicit solver that can make steps of any size, not by tick, but just like let's adapt the size delta changes depending on the error. Again, adapts if you're using implicit solver. So, and also this fully decoupled from the input data dimension, right? The dimensionality here can be fixed as hyperparameter, and the same thing can be used on any kind of input, speech, image size, and stuff like that. The internal loop is rotating internally independently of what's happening here.
So for the maze, the latent dimension would be 2D because it would be like X and Y?
No. This is only output is 2D.
Oh.
Yeah. But how the data gets in, it could be the entire image. Because the input data for the maze is black and white image. Well, it's not black and white, it's 3 channels, RGB, because one of the points on that image is red, another one is green to indicate. So, but only on these 2 pixels. The rest is black and white. That's input for the maze. Yeah, we'll get there, I hope. Fully coupled from the input data. Okay, so then post-activation history, you store everything, full trajectory of the network latent state from the start to the beginning, no sliding windows, everything is stored. Grows and grows and grows, unbounded in length. So captures temporal dynamics across the entire thought process. This is not how humans work, but okay, our animals, we don't have those resources for unbounded growth. And well, also we can start writing. We did 5,000 years ago. And the matrix is the raw material for neural synchronization. This matrix is neurons per unbounded time. Of course, we don't want time unbounded. We want to finish quickly. We want to finish not just quickly. We want to finish as fast as possible given the difficulty of the problem. If the problem is easy, we want to finish quickly. If the problem is hard, we don't want to finish quickly and give a wrong answer. We want to spend enough time and only then give an answer. They do that. This system does that. And that's interesting for us because that's what we've done with Mind Over Body paper, the iClear paper from our last year, Reynolds paper. Then neural synchronization, yay, just in the products as correlation or cosine distance, or whatever you prefer to call it, D by D. They say, well, D by D is too large. If we use, thousands and like the dimensions, then that will be too large. But SIJ measures how synchronized neurons IJ are over time, by time t, by the current time, how synchronized they are, right? And since the current time is just 1 tick, it will quickly drown. It's like 1 sample at a time. It's drown in the history. Inspired by biological neuron synchrony as a coding mechanism, spike time-dependent plasticity, STDP. And central representation replaces a static vector. Now, this is the embedding that our model operates from. Functional network connectivity is a good classifier for a reason. It compresses a lot of information. So they're saying, well, let's, and this is worth posing on. On one hand, they're saying, let's build a model that is highly dynamic. On the other hand, they're saying, oh, let's collapse everything into one number. The entire dynamics now is only in the correlation. And that relates to what you're doing as well, right? How can we beat that if correlation is already a powerful predictor? So, but they do exactly the same. But correlation of what is, it's not correlation of data. It's correlation of internal dynamics. That's like, you cannot figure out the correlation of internal dynamics without actually building the internal dynamics. And so it's kind of justifiable because what we do, we just correlate the data usually. And I mean, it's a powerful predictor, fine. Step 7, finally got here. We're saying attention here. Let me go, okay. The entire matrix is too large. for large states if Z vector has large dimension. So we randomly sample pairs S out and S action. We can decide how many, and that determines the size of the vector, the size of the matrix, etc. But instead of just computing, as on the previous slide, inner product between Z, so to compute the correlation, we add these decay parameters. And those decay parameters are just that. If you close in time, you have higher value. The further in time you are from the current position, the lower, exponentially lower. But how fast the exponent falls off, the degree is controlled by this Rij. Rij. So for each pair of neurons, it's its own specific decay parameter, which is nice because, well, that's what we think that gives flexibility to the system. And we think our neurons also not just identically replaceable things. Each interaction is controlled by synaptic strength, etc., etc. Good. Oops. Latent representation. Yes. Remember, we took random, but the same number of. So this vector is the size of this vector is fixed. What we'll get into this vector is undetermined. It's randomly sampled. It doesn't matter. Randomly sampled, as you know from computational graph lectures about algorithmic differentiation, you just differentiate through those randomly sampled locations. Fine. Still end-to-end differentiable model. That's fantastic. And then you project it through linear projection, say into two-dimensional space, x and y coordinate, or into 1,000-dimensional space, ImageNet class, which one of the 1,000 classes is that image, etc., etc. Q is a query vector to the data. Q is a query vector to the data that we will look at in the 9. Two subsampled synchronization matrices projected linearly. Yes, yes. Oh, sorry, I'm going faster than my bullets. I already said all that. So output the same prediction vector produced at every internal tick, number of classes or number of coordinates that we want to explore, etc., etc. And the model can change its mind as it thinks longer. Say if you're predicting class of one image, but you're running it multiple times, it's outputting prediction, every tick. But maybe we can wait until its confidence saturates or like peaks. And then the model cannot do it itself. I was digging for that. Like some external stopping mechanism should watch the confidence and say enough. But confidence can jump up faster or sooner or later, depending on the difficulty. Okay, so it can be scanning the image. There is a video for that. So valid predictions at every tick, well, they may be wrong. The valid, it's predicting, that's what I was saying. An external certainty threshold selects when to read off, when to chop the model. The model doesn't make a decision, unfortunately, only by saturating. Scale dot product attention or dot product attention, QKV, K and V, they come from the data because you are mixing the values, the features of the data. Feature extractor could be ResNet or something for the image input again. And for maze, it's the image input. You got the O, and off you go. Standard cross attention, the model queries the data. So the model decides actually with this, which parts of the data are more important. There will be videos. We will go a little over time. Sorry, I will not show you all the results, but still. So keys values from ResNet or other feature extractor. Then this O, not a good naming, but this O is concatenated That's how data gets into your internal dynamical system. It's back into internal dynamical system. Or the prediction, by the way, look at this. The data that the model decided to look at this current time point does not affect the output of the model at the current time point, the divergent path. It affects only the next output because this output Y came from here. It's not affected by the data. The new, like the model says, oh, move the attention over there. I want to see if there's a tail there to tail, if it's a cat or a dog or something like that. But, yeah. How do we train it? That's an interesting approach, relevant again to our work with Mrinal, because we want models that are adaptive to the difficulty to the input of the input, not ballistic but adaptive. So we take the loss value, say cross entropy. We can just say, here's my maze, and treat each location of the maze as a class. And you need to predict which next location you need to be at as a softmax over, say the maze is 39 by 39, do the math, or okay, 40 by 40 is easier, right? So 1600, 1600 points, softmax, and which one of them, so you can use cross entropy. This is this T1, at which time point in that window that you're tracking right now in the sliding window, your loss is minimal. And T2 is at which time point in this tracking window your confidence is maximal. And this teaches the model to put them together. So you want your loss and your confidence kind of align, right? You like so you like, okay, my loss is the true thing. When the model operates in wild, it doesn't have the loss because it doesn't know the truth. It doesn't, like you can't compute loss because you don't know the graph. But the hope is that the confidence will track the loss, and then we can like the confidence is actually the probability of the model being correct. You all took my course. It's in the calibration. That's actually amazing. This is what I said: minimum loss, maximum certainty. Most confident implements native adaptive computation without explicit restriction on which ticks to use, because then it has to, through this loss, it has to match those. The bad thing, the dirty secret. Now you understand this video. It's everything. The dirty secret that they don't kind of talk about too much. This is all trained by backpropagation through time. So they need a lot of memory to train to store all. This is like kind of like new kind of RNN, like an LSTM and GRU. They all RNNs. They're just this block that goes through time. It's only backpropagation through time. If only we could train them with fixed point operations like before. So Alex is asking, is it like the local dynamic programming? No, I don't think so. If it learns to do dynamic programming, then it will start doing local dynamic programming. But there will be a demo. I mean, I will share my slides eventually. Compute local dynamics with overlap to figure out horizon. Okay, results. I know we're over time, but we started at 1:12. Something interesting. Let's skip that. But here's a good demonstration. Thinking about mazes. So it starts at the red point, and there is a horizon window. Look how the red point jumped. It figured out what the best point to be, and then teleported there, and then started again sequentially. So it goes by window by window. In the bottom, you're seeing this attention. It's 16 head attention, I hope. Yeah, 16. And where the model is attending in the maze. The maze is given to the model as an image, as pixels, black and white pixels. So the bottom is interesting. It's looking around simultaneously, like it's scanning with attention. Okay, this data will be useful, or that data will be useful, and it's exploring and converging, hopefully. The beautiful thing about it, despite my bad slide where the title is beyond the under the video, is that you can train this model on 39 by 39 grid and then apply it to 99 by 99 grid, and it perfectly generalizes. It learns the function, it learns the algorithm. Well, I said it too strong. It's a wishful thinking. We hope that it learns the function, it learns the algorithm, but that's kind of the point of that. We got stuck.
We to say that it is learning some kind of greedy algorithm. It is not necessarily leading it in the right direction. Not always. It's like you can come up with a tricky maze where you can think you can go in this direction in the very beginning, and it leads you in the wrong direction.
No. Yes and no.
Smarter.
Yes and no. It sees the entire maze, but it can act locally. So it doesn't mean it sees the local. It can see the entire thing, and it can be more guided. Yes, it's not.
Okay.
I mean, it's kind of reminiscent of what you said of greedy, but because it sees the entire maze at once, it's different. Yeah. And it can decide where to look at in the maze. And the fact that I'm excited about this paper doesn't mean that it's like really good anyways, or novel or honest. It's a line of research, like nothing is new under the sun, but like they introduce a variation of it, so it's interesting. So what they did is, let's decouple, let's not take input and output like at every tick. Let's allow the model to evolve inside before the data comes in. LSTMs can do that, RNNs can do that. And they compare with RNN, LSTM, and their own model, how many ticks they allow the model to take before it outputs the answer in the next allocation in the maze. This is still the maze problem. And they say, the claim is, okay, LSTM doesn't benefit much from the number of internal ticks of thinking, and their model benefits from internal thinking. So it loops 75 times before it outputs and takes new data. It loops, so that's kind of like a convergent. Too many steps though. Could be converging quicker. So it's a convergent computation. So it's computation rather than function mapping. In computation, again, in the limit they're equivalent, like a Turing machine computation versus, or lambda calculus versus recursive functions. Even not recursive functions because you can unroll, but still more efficient. Anyways, accuracy, I don't want to talk about it, monitor blah, blah, blah. You can look at my slides later. This is ImageNet, a classification problem. So the output Y that it outputs is a vector of 1,000 dimension, 1,000 classes, and 16 heads are scanning the image. There is no X and Y output. It's just 16 heads are scanning the image in time, and the confidence changes. And this is the class that is changing of what Husky or whatever it's trying to predict, and the confidence grows with time as the heads have explored the entire image. That's this is the didactic slide, especially for people who looked at calibration of neural network. You want a perfectly calibrated neural network to be on the diagonal because you want probability of the class of correctness be equal to the confidence, the score that the network gives you. So dash diagonal line is ideal place to be, and our blue line is CTM. Currently, it's closer. I want to see logistic regression there, but anyways, so it's closer to the diagonal, right? And here they're saying, look, with ticks, with more thinking, with more iteration, the model becomes better and better calibrated. Remember what we want. We want the model to stop because it doesn't have the ground truth, it doesn't have the loss, cross entropy or anything, but we want the model to stop as early as possible when it has the highest confidence, but not earlier. So we want the model to adapt so that if it's confident, then it's correctly, then its confidence maps to the probability of correctness. Calibration, certainty, I'm rushing a little bit, but I assume we'll skip this slide. This didn't work. We'll skip this one. They did something that I not fully understand, like what's the purpose of having two plots like this. But they showed the examples from ImageNet to humans and measured the delay in the classification. By this delay in their classification, they organized the ImageNet examples into difficulty categories from 1 to 7. How fast you recognize, oh, it's a frog, versus it's a dung beetle of the specific kind and stuff like that, right? And then they're saying, hey, look, CTM correlates well with the human because it thinks, and when it reaches the maximum or whatever threshold confidence, we predict. The model doesn't stop it, we stop it, but we predict. And the time that it takes to think correlates with how, in confidence as well, correlates with humans. But LSTM also correlates with humans. So I don't know. Yeah, I don't know what they're trying to state. This is wrong. And we can play. Remember, we start from red, and we need to get to green. Okay, it found a place here. We teleport here. Oh no, okay. Explore. Oh, it's stuck. It runs in the browser, this model right now for this small size.
It looks like it's finding the same place.
I think it's stuck. Yeah, let's try. Teleport. Well, it's solved it. Yeah, now it's solved it. But it's a real demo working in your browser. Well, too easy. No. Oh, okay. We can start from here. Then teleport to the current best solution. Then teleport to the current best solution. And look at the attention, where attention is looking. You can play with that. It's in the blog post that I linked. Then you teleport. It goes away. Well, anyway. Takeaways: neurons have history. Each neuron sees its own pre-activation trajectory, not just the current state. And then synchronization. I'm kind of confused by this. Storing the sliding window. LSTM stores everything in internal state, and here it's like we have a notebook of we have a recording of our past. Yeah, maybe more parameter efficient. Synchronization is the representation, very familiar with us. Functional network connectivity and correlation matrices are very predictive, so that's what we're doing, the representing, but only the internal. More thinking, better answers. Yes, this is what I want. I want less thinking for easy problems, more thinking for hard problems, and so it's dynamically adaptive. And adaptive computation emerges naturally through their loss because they're encouraging the loss to match, the confidence to match the loss value. But they're still doing back propagations through time. I'm crying, it's too bad.
By the way, I thought that this model can work almost on a whole sequence at the same time. It's like if you ignore the outputs, picking the outputs to the model, then can process the time series all at once.
Yeah, well, some feature vector needs to give you, it will be scanning through time series back and forth, yes. If you give it as an image, for example. Yeah. The dynamics is not about the data dynamics. In real world, you don't have all time series at once. It's happening to you. They didn't show how, or I didn't find it, how it works in a robot that is acting when the time series is not there. But yeah, just give it as an image and it can scan back and forth.
So yeah, you have to do backpropagation through time because you are feeding the outputs.
It's not about the data. It's about the internal dynamics. Even on image, you have to do backpropagation through time.
Okay, that's the interest of that you can.
You have a sequence. You have dynamics. It's time, ticks. Yeah. And at each of them, the loss changes, the prediction changes, and everything. Yeah, but like a very interesting take on RNNs, and I don't know. I like that paper, and I like this research direction. I think there is more to it than continuous thought machines, even maybe simpler models that are more powerful, and then we can stack them and we can combine them. This is just one unit, right? What about one on top of another, multiple feedback loops? One is slower, one is faster, and things like that. That's how brain works, supposedly. But thank you, and thanks everyone for listening. Let me stop the recording and be done about there.